Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 212. Let's actually jump into it. We have a lot of examples to get through today. So let's actually jump into it. So as you know, our test is on Saturday. No new information to give on that at this point, so we're just going to continue with covering the material that we will need for the test. So the plan for today is to finish talking about series convergence test, and then I'm also going to talk about your approach to series, when you should apply which test, because by the end of this class, we're going to cover like 9 different series tests, and we covered a very similar number of integration techniques. And so at the end of the day, one of the most confusing things is just knowing when to apply which technique, when to apply which test. And so that's essentially what we want to cover today. Finish talking about all the tests and then figuring out when do we actually apply which ones. And that's pretty much the plan for today. And tomorrow we're going to move on to things like series estimation. And I think we'll probably even start talking about power series. So let's actually get into it. Quick recap, remember a series is just the sum of the terms of a sequence. We care about infinite series, so we're adding up an infinite number of terms. Ever so often, this infinite sum seems to add up to something that is meaningful. It adds up to a real number in a meaningful way, and we want to determine when will this happen. That's going to be very important. Essentially, we know several series tests, which are summarized in the table here, which you can also find at this link on the math department on our class's webpage. And these are the guys that we're going through. I think last time I covered up to the P series test. We stopped just before the P series test. So now we're going to actually finish up the rest of this table. You were overthinking what a series was? Yeah, that's all a series is. It's just the sum of the terms of a sequence. You're just adding up a bunch of terms, right? So series is, you can think of it as sort of a generalization of addition, like you're just adding stuff, except you're not like adding 5 things together or 10 things together or even 1,000 things together. We really want to talk about adding an infinite number of things together and whether or not that is meaningful, and if so, what is the meaning and how we can apply it. So that's what we're doing. So there are a bunch of tests that will tell us when a series will actually add up to something meaningful in some sense. And remember, there are 2 senses in which a series can add up to something meaningful. There's absolutely and conditionally. We are going to talk about both of those later on today as well. But yeah, so last time we spoke about a couple tests, the test for divergence. And as the name suggests, remember, this can only tell you about divergence. Cannot use this test to test for convergence, right? So basically, if the sequence terms, the limit of those guys does not approach 0, it means that the series does not converge. We also spoke about, and we did a bunch of examples there. We also spoke about the harmonic series with one specific example. We also spoke about the geometric series test, which is applied to geometric series, which are the guys defined here. And we looked at when those guys converge. We also saw that they converge absolutely. And absolutely just means they converge with absolute values put around the sequence terms. And then we spoke about where is it? Okay, we spoke about the integral test, which is basically using our knowledge of improper integrals to determine what's happening to series. It turns out that when a series has a corresponding improper integral, you can actually use the improper integral to determine what happens to the series. What does it mean that it has a corresponding integral? Well, it means that all these criteria are fulfilled. You can think of your sequence as a function. If it's continuous, positive, and decreasing, and you can integrate it, in theory, we can apply the integral test here. So we did one example of that, which was fine. And we sort of ended with the P series. So that's where we're going to pick up with the P series. So started here on 622. All right. So now we're going to jump in. We're going to cover the rest of the series tests in that table. I'm going to tell you how they show whether or not a series converges. We're going to talk about, again, kind of emphasize some things on absolute convergence versus conditional convergence, and talk about when you should apply which test, because individually, none of the tests are in and of themselves complicated. The complication comes in when you don't know which test to use to come up with a certain conclusion. So the next guy we're going to jump into is the P-series test. And this is, all again, a series that's of a specific form. It is 1 over n raised to the p power, right? Where p is a constant. And it turns out that if I think of this as a function, so I think of the function 1 over x to the p, that guy is continuous, it is decreasing, and it is positive for all x greater than 1. And so what you realize is I can actually use the integral test on that series to determine when it converges. We also saw that there was a theorem that we covered a couple lectures ago, that this guy converges if and only if the p is greater than 1. So basically we end up with the P-series test. A series of this form converges if and only if p is greater than 1. So if you have a series, n goes from 1 to infinity, and really n can start from any number, but the standard way to consider it is to go from n goes from 1 to infinity of 1 over n to the p. It will converge if and only if your p is greater than 1. And your n can start at, as I mentioned, any number larger than 1 as well, and would still work out. And you can just kind of use a sum of series to determine that. Maybe I'll talk about that in a little bit. So remember, the harmonic series has p equals 1, and so it diverges. So there's another way that we can see that the harmonic series diverges. We can show that that diverges by the integral test as well. 1 over n squared actually converges by the P-series test. And we saw last time that that converges to pi squared over 6, which was not obvious at all. So right now, there's really nothing else to say about the P-series test. It's just, if you see that form, just determine what your P is, and it will converge if your P is strictly greater than 1. No, when it comes to a P-series, you don't need to do the integration. The integration happens in the background, and it makes this conclusion. When it comes to a P-series, what's in the box is what you need to know. If your P is strictly greater than 1, it converges. If it's not, it diverges. And there's nothing else to say. Now, the reason why that is true is because we can use the integral test on a P-series. But you don't need to do the integral test for a P-series. Just do the P-series test. So when you combine the integral test with that theorem that we had, the integral of 1 over x to the p converges if p is greater than 0, strictly greater than 1, we get convergence. So here are a couple series, not many crazy examples here, because P-series in and of themselves, like I said, they shouldn't be difficult. And the thing is, almost never will you be given one of these guys directly. We are going to use these guys in other things like the comparison test. So let's actually jump in. What do we think about this series? Let's look at example part A here. Diverge, how do we know it diverges? Because your P equals a half. Yeah, so that's essentially it. There's nothing else to do here. So realize that this just means, this is just another way of writing the series, 1 over n to the 1/2 power. And so here you'd realize that your P is here, P equals a half. And so basically, once you rewrite it as that, you can conclude the series diverges by the P-series test. Since P equals a half. And that's it. Nothing else to say here, actually.
Why not the comparison theorem?
What?
Why not the comparison theorem?
Well, for a couple reasons. One, using the comparison theorem would be harder. Why would you do that if it's just easy to just see what the number is? And two, we haven't covered the comparison theorem yet.
And about the comparison test, like, you know, limit comparison test, direct comparison test.
Right. And I just mentioned why we would not do that. One, it is harder to use. Why would you go for a harder method as opposed to an easier one? And two, we haven't covered the comparison theorem yet.
And plus, why not the integral test? Like, you know, it diverges by the integral test.
It does. But again, the integral test is harder to use. Why would you do that? because to conclude that this would diverge by the integral test, you're going to have to set up an integral and compute it, right?
Yeah, I mean, like you would get like 1 - and you also, if you were to take the integral, you would get two and a half. And if you were to plug in the endpoints 1 to infinity, you therefore would diverge.
Right. And so why go through all that trouble when I can just look at this and see, hey, there's a half right here, so I know the answer.
It's all because of one simple reason, because this is a very easy and basic step, and looking at
Yes, it's all
basic approach.
because this box tells me everything I need to know, and it does not require an integration. Right? So you shouldn't be afraid to work hard, don't get me wrong, but working hard when you don't have to is silly. Like there's no reason to go through all that trouble. Right? I can just see here the power is a half. It diverges. Like why would I need to go through an integral or find some other series to compare it to when I can just actually look at it and eyeball and know the answer? It's just not worth doing anything else. Right? Here's another example. What about this one? What do you think?
This converges because if
You're,
you were to think about it as a fraction, you would have 1/11 to 1/n to the 11/10 power, and therefore anything greater than 1, it converges according to the p-series test,
right.
because 11 out of 10 is greater than 1 if you were to divide
Right.
you know
This
11 with 10.
is a convergent p-series since your p is equal to 11/10, which is strictly greater than 1. So that's going to be your answer. Okay, that's it. That's the p-series test. Nothing else to really talk about there. So it's easy to see when it works. It's also easy to apply it. And so the thing is, we're almost never going to see a problem with that just has the p-series test coming into play just by itself. We normally use p-series when we actually want to do a comparison. So let's actually talk about the comparison theorems, or the comparison test rather. Right, so remember that we had comparison theorems from improper integrals, right? We had the direct comparison theorem from improper integrals. We also had the limit comparison theorem from improper integrals. Again, using the integral test in the background and comparing a series to an integral, we can apply the comparison theorems for improper integrals to series. And so when we do that, we call these the comparison tests. And so we can actually do a direct comparison for series as well. And so basically, what we get here is, here's one of the comparison tests called the direct comparison test. We usually leave out the word direct whenever we say a comparison test. If someone says, I'm using the comparison test, we assume they're talking about the direct one, okay? So again, here, you're looking at a series where the sequences are positive and you know how they're ordered in terms of inequalities. So if an is greater than or equal to 0 and it's less than or equal to bn, for all n past a certain number, then the sum of an is less than or equal to the sum of bn. And on top of that, a very similar conclusion to the comparison theorem for integrals holds. If the larger one converges, then so does the smaller one. If the smaller one diverges, then so does the larger one. And in other cases, you can't really make a conclusion because we can't tell. For the same reasons that the comparison theorem for improper integrals made sense, this thing makes sense for exactly the same reasons. Okay, so here is something. Determine whether this series converges. And right now, it's already starting to get a little hairy, right? Look at this. It looks very complicated. Oh my God, look at that. So crazy. Like, how are we actually going to do this problem? Okay, so what do you think? So here's something that we can actually use the comparison test on. Any ideas on how to actually do that?
If you were to think about like this, for an expression like this, like this series test like this, you would obviously think about the direct comparison test, and you would think about it. Of course, when I point to the comments, I see like break up, like for a
How
problem
would you
like
break
this,
it up?
for a problem like this, write down 3k
Yeah,
over, you see the square root.
yeah.
2k 5 times half, you would get 2k to the 5 over 2 power plus 2k, to the first power
Okay, so
times.
you cannot break it up like that. And in fact, you're doing two major mistakes at the same time here. For one, radicals do not distribute across sums. This is a blasphemy. So we can't do that. And two, even if we could, you cannot split a fraction across the denominator. We saw this again last class. You cannot, like if you have a sum in a denominator, you cannot break it up. That's not the same as this, right? That's not true. You
I'm
cannot
not
break up
saying like that. I'm not saying that. I'm just letting you know is that the half is 2k 5 power times the half, just multiplying the half, each of the coefficients and the constants, just multiplying
Exactly.
by a
And that
half.
is distributing across sums. Like if you have the radical of A plus B plus C, it is not the same as radical of A plus radical of B plus radical of C in
I'm
general.
not splitting and separating it like that. That's not what you think. Multiplying, here's what I was talking about. You see the half, right? Just multiplying the half to each of the numbers, not
Right. And what would
splitting
you
it up.
get?
However, you would get 2k to the 5 over 2 power plus 2k to the half power, and the 1 to the half power would just be like 1. It's just like the square root of
So you're
1.
saying the denominator would turn into that?
Well, according to what I'm assuming, and also
Right.
plus
And
you have the
that's what I'm telling
numerator.
you. The mistake you just made is this mistake up here. That
You're
is
just
not true.
you're just splitting and separating the square root. You're just splitting it
Right.
up.
A
I'm not.
square root is a power. You cannot distribute powers across a sum. It is not true. It is incorrect. That is
So
not algebraically correct.
so 3k, and according to what I figured out, how it converges is all because 3k, and you have the square root, 2k to the 5 times the half. You get 2k 5 over 2 power, and you have the 3k as the numerator. If you were to cross cancel it, you would get 3 over 2 k to the 3 over 2 power. And therefore, you could already figure out, well,
Okay,
it
but how would you
converges.
get to that point? You can't actually get to that point doing what you're doing. You're overthinking it, and you're also doing things that are algebraically incorrect. Like it's not true to think the way you're currently thinking. It's actually not mathematically, it doesn't make mathematical sense to do what you're doing.
And according to what you see here, the 0
Anyway,
less than
so
or
the
equal
thing
to
is,
a.
again, you want to think in terms of like the strategy that you do with limits. So you're going off to infinity. Now there are a couple of things. Only the bigger guys are going to matter when you're going off to infinity. So that's what you're going to think about. So you are going to want to imagine that you're only looking at the series 3k over 2k to the fifth with a square root under it. Of course, k equals 0 is going to be a problem. So before that, we can just recognize this is actually the same as the series with k equals 1. Because by plugging k equals 0, it makes no difference.
So what I want to tell you, Jhevon, is speaking of one of the formulas that you saw earlier, 0 less than or equal to a to the base n less than or equal to the b to the base n.
Right.
However, your a would probably be like the 3k, and the b would just be the 2k to the fifth power plus 2k plus 1. Therefore,
Essentially, what you're going to end up here with is this guy that you care about is going to be less than or equal to this guy over here. So we're not saying they're equal because they're not. They're potentially less than or equal to. Why can I go from k equals 0 to k equals 1? Well, look at this original series here. What happens when I plug in k equals 0? If I plug in k equals 0, what do I get? No, I get 0 over 1, right? I would get 0 in the numerator, and there's a plus 1 in the denominator. I would get 0. Plus, then I'd plug in k equals 1, and then I'd get something else. Plus k equals 2, and I would get something else. So essentially, the k equals 0 term doesn't add anything to the series. So I can literally just ignore it. So then I can move into this position. Why do I want to do that? Well, notice what I'm comparing it to over here. If my k was 0, that would be an issue. So I had to figure out a way to not have the k equals 0 come into play. So that's the first thing. So the first thing is just make sure I'm not dividing by 0. I'm going to want to actually change things. Then you're going to look at the highest powers, and you're going to want to compare it to the thing with the highest powers. In this situation, because the series on the right over here has a smaller denominator than the series on the left, I know that this guy is larger. On top of that, now if I look at this guy, look at this series right here, what's going on with that series? This guy I can actually rewrite as, I can factor out a constant, and I would have k over k to the 5 over 2. Right? And what kind of series is that? It's a p series. In fact, I can simplify this by just subtracting the powers. So 2 over 2 minus 5 over 2, this is 1 over k to the 3 over 2. So now this is a convergent p series. So now I just showed that I found a series that is larger than the series I care about, and it converges. This allows me to use this line in the direct comparison test to conclude that my original series converges. So and you can even say by comparison with the series 1 over k to the 3 over 2. Okay. So I see something like this. My mind is going to gravitate towards just looking at the guys with the highest power. Why? Because I'm going off to infinity and all the lower powers aren't going to matter. So if I get rid of all the lower powers, I obtain this guy, and I know for sure that that is going to be larger than the original. Why is that larger than the original? Because the denominator is smaller. Then I focus my attention on this guy and notice that it's a p series. Those guys are easy to spot when they show up. So I can show that that guy is convergent by the p series test. And so this guy will have to converge by the comparison test, because I just showed that there's a series bigger than him that converges. And both of them are larger than 0. So this allows me to apply the direct comparison test. I just set up this inequality right here, where my bn is the 1 over k to the 3 over 2. And the an is my original series. So I found a guy that's bigger, that converges. So the direct comparison test will tell me that the original series converges, right? Now, if I wanted to show diverges, what I would need to do is find a smaller series that diverges. But we'll see more examples of that later on. But that's basically the direct comparison test. Theoretically, the ideas are very, very similar to the comparison theorem for the integral test. So if you understand that, you will definitely understand this. Of course, one thing you do not want to make sure that you're not falling victim to is algebraically simplifying things incorrectly, because that's a very common mistake, and that can lead you to the wrong answer sometimes. In the same vein, we can talk about the limit comparison test. So it's not called theorem, we call it the limit comparison test. So let's actually do that. So the limit comparison theorem, this reminds us of the limit comparison theorem that we have from the improper integrals. But here we're looking at series, so we tend to call it test. Okay. And again, very similar. Suppose you have two guys that are positive, two sequences where they're always positive. If you take their ratio and take the limit and you get a number, you can determine what happens to the series. You can determine what happens to the series based on what that number is. We have a question here. No, the denominator, you can't have a zero in the denominator. It doesn't matter if it's under a radical or not. You can't divide by zero. Yeah. And once you have something like you're dividing by zero, the limit like doesn't exist, then it would diverge by the test for diverge. Anyway, so there's a limit comparison test, very similar to the limit comparison theorem for improper integrals. Take the ratio of two things, look at the number that you get when you take the limit. If the limit is a positive real number, then the series that have that ratios, they will either both converge or they will both diverge. Now, there's an additional, some additional facts you can add here, but it very rarely shows up in a Calc 2 class where you need to know these two facts. I put them there just to be comprehensive, but pretty much if you know what's in this box here, that's the level at which I expect you to be able to apply the limit comparison test. So take the ratio and they will both do the same thing if you get a positive number. So again, here is where you're given one series and you have to find another series to compare it to. Just like here, I was given this series and I found some other series to compare it to. That's why it's called a comparison theorem. You have to find a whole other series to compare it to. So here's one right here. Determine whether this series converge. Right? So I have this guy. Now, of course, going by the same intuition that we had before, I can just realize that, hey, I kind of only want to focus on the larger powers. Focus on So I'm going to focus on these guys right here. So ultimately, I want to compare to a series that looks like 1 over n. Okay? Now, here's the problem. How do I know if this is bigger or smaller than this original guy, right? So notice here, we're not sure, however, whether this is larger or smaller than the original. And to answer a question, no, you cannot plug in test values because remember, you're going off to infinity, right? So you can't just plug in a few values and check because someone can make the argument, oh, you just didn't plug in the right number. There's an infinite number of numbers to plug in. Like if you're going to prove one is larger than the other, you are going to have to do something a little bit more sophisticated than just plug in numbers. One of the simplest ways you can do something like that is plug in a number to show that, okay, at this point, one is bigger, and then you can find derivatives to say, well, the slope of this one is always larger, so if it starts out bigger, it'll always stay bigger. But again, that's going to be a lot of work, something more sophisticated. Right here, notice that I can't tell immediately whether this is bigger or smaller because the numerator is smaller, which leads to a smaller fraction. And at the same time, the denominator is smaller. And this leads to a larger fraction. And so now the idea is who actually would win out, right? Did I make it smaller than in magnitude than I made it bigger, right? Who wins? To actually determine that, you're going to need a little bit more sophisticated argument. You can't just plug in test values to determine that. So we're in a situation where I know exactly the guy who I want to compare it to, but because of jumping from one guy to the other, I'm just not sure who would be bigger or who would be smaller, which for the direct comparison theorem or the direct comparison test, I actually need to know who's bigger or who's smaller. So here, I don't know who's bigger or who's smaller. So I'm going to apply the limit comparison test. Because the limit comparison test doesn't care who's bigger or smaller. So I'm going to think of my AN as the original guy, say n plus 10 over n squared plus 2n plus, I think it was 5. 3. And my Bn is just 1 over n. Now what do? I'm going to find the limit as n approaches infinity of an divided by bn. Well, that's just going to be the limit as n approaches infinity, obviously, of n squared plus 10n over n squared plus 2n plus 3. And so that is equal to, what is that limit? It's 1. 1 is greater than 0, which means both series do the same thing. And so now it means if I know what happens to one of these series, I automatically know what happens to the other. Well, I took an divided by bn. If I divide by 1 over n, keep, change, flip, it's the same as multiplying the numerator by n. Right, dividing by a fraction is the same as multiplying by the reciprocal. So it ends up being multiplying the numerator of the original by n, right? I'm not saying you can't use the comparison theorem. I'm saying this is a consideration if you want to use the comparison theorem. And then that means you would need to justify that you're able to use the comparison theorem. You would then have to be able to prove definitively that this guy is actually less than that guy if you want to use the direct comparison theorem here. Yes. If you didn't have the plus 10 in the numerator, then for sure this would be large. Then for sure this would be larger. 1 over n would actually be larger, in which case you couldn't conclude anything anyway. So both series do the same thing, but look at Bn. It's a divergent P series. This means the series AN diverges. Right? So I see a guy like this. That's too complicated, too much stuff going on. So I want to simplify. How can I simplify? Well, just ignore all the lower powers, because if I'm going off to infinity, they're not going to matter. If I do that, I get this guy. Now I would need to know how does that guy compare to this guy to apply the direct comparison theorem, but I don't immediately know without having to take extra time and effort to prove who is bigger and who is smaller. So I decided to, let's just not do that. And let's just jump directly into the limit comparison theorem, because this theorem doesn't care who's bigger or who's smaller. So by applying the limit comparison test, the ratio gives me a positive real number, and so I know both series do the same thing. Bn is a divergent p series, and so my an diverges. I wouldn't say they're equal to each other. They don't equal each other. They're not the same. I mean, technically here they both add up to infinity, but it's not because they're exactly the same numbers all the time. This fraction and that fraction actually gives different outputs for each n. However, this one is easy to tell what happens to it. It's just a p series. And yes, it starts from 3, but a p series, we can just use a p series to determine it. We can just use the first, yes?
Why couldn't we use like, the direct comparison theorem like in this problem? And how come in the last problem we didn't use the limit comparison theorem?
Because of reasons that I explained here in blue.
I mean, like, not sure whether this is larger or smaller than the original because the number is smaller.
The numerator.
The numerator is smaller in the smaller fraction, like, denominator is smaller in the larger fraction.
Right. So to go from this to that, I both made the numerator and the denominator smaller at the same time. I subtracted 10 from the numerator to make it smaller. And then I subtracted the 2n plus 3 from the denominator to make it smaller. So both the numerator and denominator decreased in size. When both of these changes happen at the same time, you don't know which change is going to win.
Easy way to identify is when the numerator or the denominator, or maybe even the exponent of the numerator is less than the denominator. Therefore, we can identify whether or not if it's by direct or limit comparison.
No, you would first ignore everyone except the lower powers. That is step 1. Step 2, you need to determine who is bigger or who's smaller. If you can determine that easily, do direct comparison. If you cannot determine that easily, do limit comparison. So that would basically be it. Because the limit comparison doesn't care who's bigger or who's smaller. So if you don't know, it doesn't actually matter. For the direct comparison, you do need to know for sure who's bigger and who's smaller. And you can only determine convergence if the larger guy converges. You can only determine divergence if the smaller guy diverges. And in all other scenarios, you don't know. So in this case, the limit comparison test is the better test to use. Let's move on. Test 7. We're going to look at the alternating series test. So by definition, an alternating series is just a series where the terms alternate signs. So you have something like a minus a1 plus a2 minus a3 plus a4 minus a5 plus a6, etc. Or you have a plus a1 minus a2 plus a3 minus a4, right? Each term alternates in sign. So the terms are all positive, and then you can apply a plus or minus sign alternatively. Once you have such a series, this is called an alternating series. A very common way to write these guys down is something like this, a minus 1 to the n. This is a guy we looked at before. Right, minus 1 to the n times an an, that defines an alternating series. That's how we would normally look at it. So that's how you're going to see the definition. So now, this test is surprisingly simple. Basically, you're going to determine that if your terms are decreasing and the limit goes to 0, then the series converges. And that's it. So these guys here, you would find the limit, and you need to know that the terms are decreasing. And remember, we also spoke about that. So decreasing means, remember what decreasing means? This means that you can show that an plus 1 is going to be less than or equal to an, or you can show that a(n) prime is less than 0 if differentiable. So as long as eventually it's decreasing, you can apply this test. And this guy is really nice because this allows you to just determine what's happening with a series with a limit. You just take the limit. So you can only do this when it's alternating. In general, the limit being 0 doesn't tell you anything. However, for alternating series, if the terms are decreasing, if the a(n) terms are decreasing and the limit approaches 0, you can conclude that it converges. Very, very important warning here. The alternating series implies that the signs are alternating, which means you need the negative guys in play. Okay? Now, what does that mean? This means you cannot actually use this test to determine absolute convergence. So absolute convergence is, remember, when you put absolute values around all the terms, and then you see if it converges. If we put absolute values around all the terms, then it's no longer an alternating series, and we are not allowed to use this test. So this test can only work if we don't have any absolute values messing with anything. So once the signs are alternating, if the terms are decreasing in magnitude, then we can, the name of this test is the alternating series test, because it applies to alternating series that looks like this with alternating signs. So once I realize I have an alternating series, if the terms are decreasing in magnitude and the limit goes to 0, then the test will converge. You can only determine conditional convergence from this test. It cannot tell you about absolute convergence. Very common mistake for students to make. That's why I put it in red and underlined it. So here's an example. Not meant to be complicated. We'll do some more complicated examples later on. This one is just meant to introduce the idea. However, it's also a very famous example. It is the alternating harmonic series. This guy does converge, by the way, converge conditionally. In fact, this guy equals, believe it or not, minus ln2. Obviously, right? But we will actually look at determining that this guy converges. We won't really know necessarily what it converges to by this test. However, it is a famous series, so I decided to actually introduce this topic with this guy. So here, note, the series here, minus 1 to the n over n goes from 1 to infinity. This is equal to minus 1 plus a half, minus a third, plus a fourth, minus a fifth, plus da da da. Notice that now it's an alternating series. Right? Because the signs are alternating for each term. So this means if I set a(n) to be equal to 1 over n, which is what it is right here, I can see that a(n) is decreasing. That's pretty obvious right here. And the limit of a(n) is equal to 0. And once I do that, it means the series a(n), or more specifically, minus 1 to the n a(n), converges by the alternating series test. And that's basically it. It's decreasing. Here it's pretty obvious that 1 over n is decreasing because the numerator stays still and the denominator is increasing. So now just find the limit. Limit equals 0 means it converges. Now, what happens if we put absolute values around all the terms? And again, this is going to be an idea we will be exploring later. So if we put absolute values around the terms, you would have the series n goes from 1 to infinity of the absolute value of minus 1 to the n over n. That is just going to be the series as n goes from 1 to infinity of 1 over n. This guy is harmonic. This essentially means the series here converges conditionally. Right? So if I put absolute values around it, it does not converge, which means it does not converge absolutely. So I throw absolute values around it. So i.e., the series is not absolutely convergent. Because when I put absolute values around it, it doesn't converge anymore. However, by the alternating series test, it does converge, which means it has to converge conditionally, right? So the alternating series test can tell you about conditional convergence. It cannot tell you about absolute convergence, right? Yeah, and so that's a simple example. You see alternating signs, you can apply the alternating series test, and you have to look for two things. Is the guy decreasing or eventually decreasing? And does the limit goes to 0? If both of these two things work out, when we're alternating signs, then the series automatically converges. And it's very important that you know you cannot say it converges absolutely for this reason alone. You need additional information to know that it converges absolutely. But sometimes you want to just check conditional convergence, and this test is good enough. And so that's that. So you see signs alternating, check if the guys are decreasing in magnitude, check if the limit goes to 0, and that is in and of itself a test called the alternating series test. So here is test number 8. Very, very important test. In fact, we're going to use this test to do things other than just tell whether a series converges. So very, very important test called the ratio test. Let's move him up here. And we're going to do 2 examples for this one. Okay. So now some information on the ratio test. You can apply this to any series in general. It's particularly useful though if you have factorials and exponentials and a lot of that kind of thing going on. The ratio test is very convenient for that. The ratio test is not convenient for rational functions. So if you have a series of a rational function, not convenient is actually putting it mildly. It's definitely not going to work. So that should just be something that you should keep in mind, and we'll talk about later as well. Ratio test, in theory, can work on anything. However, it's particularly useful when you have factorials and exponentials around. It's not going to work for rational series, so don't even try it. You're wasting your time. Here's how the ratio test, what it says. Basically, you're going to take a certain ratio, which is why it's called the ratio test. Now, as long as the terms aren't 0, so technically not any series, you want a series where none of the terms go to 0. And the reason is you're going to be doing a division with the terms. If you divide the n plus first term by the anth term, the formulas, you put absolute values around that and you take the limit, we can get this number that we call L. And based on what the value of L is, we can actually determine that the series is convergent or not. In fact, whenever this test shows convergence, it actually shows absolute convergence. We do, in fact, put absolute values around the ratio before we're doing it. So you find this limit. If the limit is less than 1, strictly less than 1, we can conclude that the series is going to be absolutely convergent. If the limit is greater than 1, we can conclude that the series is divergent. If the limit equals 1, then you can't actually make any conclusion. It's actually possible for it to converge as well as diverge. And it's worth pointing out that if your an is a rational function, like a ratio of 2 polynomials, it turns out that your limit will always be 1, specifically. because once you take the ratio of the an plus first term and the an nth term, they're going to be the same degree polynomial, and they're going to have the same leading coefficient. So you're always going to get the limit approaching 1, and it's not going to give you any conclusion whatsoever. So don't do this when it's a ratio of polynomials, when it's a rational function. Okay, but other than that, it's a very important test. Let's actually do it. So I'm going to run through the first one with you, and then you guys can help me with the second one. So here's an example. Now, let's say I want to determine whether this series converges absolutely. So I'm going to consider the series with absolute value around it. So I'm going to look at this series here, put absolute values around it. Right? And why? Because it asked me about converging absolutely. So I need to consider absolute values around it. Okay, so that gives me this series here. And so now I want to figure out, does this guy converge or diverge? Right? Now, there are multiple ways you could do this. I do also think that the integral test can work here, but it's going to be integration by parts. It's going to be really hard. So I would actually just do the ratio test. Here, I see some exponentials here. How did I get n? The n was always there. It was in the problem. What n are you talking about? Yeah, the n was there in the beginning. Me throwing the absolute values around it, it kills the -1 to the n, right? It gets rid of all the negative signs because I put in absolute values. So now I get this guy. So now this guy here, this formula is my an. So now I can actually do the ratio test, which is one of many options, but the test of the hour right now is the ratio test. So now here, apply the ratio test. So I'm going to look at L equals the limit as n approaches infinity, and of course it's always infinity because we're doing the sequences, of an plus 1 divided by an. Personally, I like to think of this, useful to think of this as for simplification purposes, as an plus 1 times 1 over an times the reciprocal, right? It's just nicer to think of it that way. So right here, what that ultimately becomes is that an plus 1 is what I get when I go to the original and just plug in n plus 1 everywhere I saw n. So here I'm going to have n plus 1 divided by 2 to the n plus 1. Then I'm going to multiply by the reciprocal of an. So that's 2 to the n over n. So this guy here is my an plus 1. This guy here is my 1 over an, right? And then I just multiply them. And so now the goal is to figure out what is this limit, which, I mean, it's a limit. At this point, it should be easy for us to figure out what that is. Now, I would say here, this is an optional step. But nice to apply for, especially for complicated things. And that is to kind of separate like terms together. It'll make you it's easier to see who would cancel, how things are going to simplify. So for example, I can put the exponentials together and the polynomials together. So I can rearrange the multiplications so that the exponentials are attached to each other and the polynomials are attached to each other. Now, it's not completely necessary to do this, but it helps you to visually see how things are going to work out better. What you're now going to notice is that the 2 to the n is going to cancel into that. Maybe I should do that as a separate step. So we have this guy. So now what you're going to notice, and again, rewriting it like this is optional, but it's nice to have it like that. So the 2 to the n is going to cancel that. So you're just going to have a half. And you can't really cancel anything here, although, I mean, it's not going to be very useful to cancel here. But now we just have essentially the limit, and you can leave off the n approaches infinity if you want, of n plus 1 over 2n over 2, because this guy got canceled. And what is that limit? No. N plus 1 divided by 2n. It's a half, right? Highest power is the same on top of bottom. It's a rational function. Goes to the ratio of leading coefficients. Now, the nice thing about a half is it's less than 1. So this means the series converges. In fact, the series converges absolutely. Does it converge? Absolutely, it converges. So I see this guy. I am asked to check whether it converges absolutely. So I put absolute values around it. I get a new series, and now I want to examine that. Because it has exponentials, and I remember, hey, this test is useful if you have factorials or exponentials. I remember Jhevon saying that in class. So I'm like, okay, let's actually do the ratio test. It might be convenient. Doing it here, do a little bit of simplification, not too much of a big deal. And now I can just determine what happens by looking at what this limit goes to. Now that limit goes to a half. A half is less than 1. According to the ratio test, if my L is less than 1, it converges absolutely. So I can actually make the conclusion it converges absolutely. And that is me applying the ratio test to this series right here. Okay. So you guys practice. Tell me what's going to happen with this guy. Tell me about this series. You see that series, what do you do? It also has a factorial in it and an exponential in it.
Wouldn't you put absolute value bars around it to cancel out the alternating sign?
Sure. And what would you get?
Yeah, put absolute values. And then you would get n factorial over e to the n.
Okay. And then what?
And then that's when you would do the ratio test.
Yes.
So your a n plus 1 would be parentheses n plus 1 factorial over e to the n plus 1.
Right, and then you're going to divide by that same thing. Now, for the purposes of this demonstration, that is exactly correct. However, if this were on a test or a quiz, you would not go down that road. So technically somewhat of a trick question I'm throwing at you guys here because, you know, I have to get my enjoyment somehow. Can you see another thing about this series? Maybe something that jumps out right away? So I am going to do what was suggested, but there's something else that I want you guys to be able to see first. Can anyone tell me what that is? Sure, there's an E on the bottom. Anyone see anything here more immediate? I don't believe we did this question before. Factor of the E to the n, factor of the n factorial, no. There's something even more obvious than that. Or hopefully it should be obvious. E to the 1 is 0? I'm not sure what that means, because E to the 1 is not 0. Okay, I'll give you guys half a hint because I don't want to spend too much time here. Don't give up.
You know how you would approach this actually?
How would you do it, Jason?
A base n plus 1 over A base n.
No, that was already suggested. That's what I'm saying. There's something else that I want you guys to see here first. We are going to do that, but there's something else that you should see first. Okay, so I'm going to tell you guys what the answer is, and then tell me a quick way to get to the answer. Ratio test is not necessary. The series diverges.
I mean, like, it does diverge.
Yeah, but why? This is a problem that you should be able to look at it and know it diverges with minimal effort. The ratio test is actually not necessary. I am going to use the ratio test to show that this diverges, but there's a much quicker way.
You know, let me guess. P-series test because of the n
No,
equals...
it's not a P-series. P-series has a very specific form. P-series looks like 1 over n to the P. We have a factorial here and an exponential. It's not a P-series. We actually covered it last class, and I mentioned last class that, hey, this is one of the first things I want you guys to look for whenever you're looking at a series. Remember that? I said that last week. Seems like forever ago.
Is it geometric?
It's not geometric, no, because it has a factorial in it. Geometric looks like a times r to the n, where a and r are constants. There are no factorials. And we don't have, because the n factorial means it's not geometric. It's even easier than the geometric. It's the very first one. Test for divergence. Limit of this guy is infinity, which is not 0, right? So this is something that you should have seen, right? There's a factorial in the numerator and an exponential in the denominator. That's not going to go to 0, guys. The terms here are getting bigger. There's no way it's going to add up to a finite number, right? So this is actually something that you can know diverges just by the test for divergence. So I am going to actually go through the ratio test way of doing this problem, but it's strictly for demonstration purposes. Had this guy shown up on a test or a quiz, if I write a test or a quiz and I throw this guy on there, I'm thinking in my head, yo, everyone's gonna get this in like 5 seconds and then move on with their lives. They're just gonna be like, oh, test for diverges, and then move on, right? But some students are gonna go into, oh, ratio tests and this, they're gonna do all these calculations and they're gonna try to figure this out and they're, oh, let's compare it to this P-series, right? You're going to want to be able to do that. And again, that's a part, I'm going to get to around to that, like how you wanna look at series, how you're gonna approach it, what do you try first, second, and third. But I just wanted to bring that up again, since I mentioned it last class that this is one of the first things you're going to want to do. A lot of the times when students are running out of time, it's because they're being so inefficient. So you want to be aware of that. Don't work harder than you have to, because a lot of the times you're not given time to work harder than you have to. You're given time to show, I've mastered the material. I know when to do what. Here's how to do this problem. You need to actually be able to prove that. But here, we'll use the ratio test just for demonstration. because there is a nice little trick that's going to happen here that I actually want to emphasize. So we are going to do it. Right? So I'm going to do the ratio test here, but I do want to point out that in the field, I would not expect you to do the ratio test. Like it's a waste of time to actually do the ratio test for this guy. So there's a much better method. That clearly does not go to 0 because it's a factorial divided by an exponential. However, if we're doing the ratio test, I'm going to look at the limit of an plus 1 divided by an. So now I can go with, I don't know who was talking earlier, if it was Kayla or someone else.
Me.
Huh?
It's your girl.
Okay, the ringleader. Okay, so let's go with that. So we're going to just go here, plugging n plus 1 everywhere we see n. And as Kayla mentioned earlier, that's going to look like n plus 1 parentheses factorial. Don't forget the parentheses, raise to e to the n. And then I'm going to just multiply n plus 1. Then I'm going to multiply by the reciprocal, e to the n over n factorial. And again, I'm going to
Group-like terms.
Group-like terms. This, like I said, this step is somewhat optional, but I think it's worth it for most people, honestly. So you can see things nicer. Now, clearly here you can see that the e to the n is going to cancel n factors of the e's in the denominator. And now we're going to do, figure out what this guy is. And this is the part of the problem I wanted to emphasize. So this is why I want to do the ratio test, even though technically I wouldn't do the ratio test here, to show the kind of trick that would have happened here. Can someone tell me what would happen for this part? So based on what we know about factorials, there's a certain behavior that we can take advantage of here. How would you deal with that part? N plus 1 factorial divided by n factorial. How would you determine what that goes to? How would you break it up? Break it up how? How do you know? Don't just tell me the answer. How would you figure that out?
Well, if you expand it, the top is always going to be bigger than the bottom because you have the n plus 1. So let's say your n is equal to 5. Your bottom's going to be n. Your bottom's going to be 5 factorial, but your top's going to be 6 factorial.
Okay.
And if you cancel, and if you expand it and you cancel all them out, you're going to be left with 6. So you're
right. So the trick here is to cancel them out. But how do you cancel? Well, just realize that the top is n plus 1 times n factorial. And then you're going to be able to cancel those two. And so now we know it's going to go off to infinity because now it's behaving like n plus 1. So that's a standard trick here. And that's one of the reasons why the ratio test is useful for factorials, because it allows them to cancel. So here I would have the limit of n plus 1 over e. And I'm going to go over that point again. And this, of course, goes to infinity, which, as you know, is greater than 1. So the series diverges. But I do want to mention, this does showcase why the ratio test is this showcases why the ratio test is useful for factorials. And that's because smaller factorials are always hidden inside of larger ones. They're always a factor. Smaller factorials are always factors of larger ones. So if I could get a way to divide a factorial by another factorial, where one is bigger or smaller than the other, it allows me to simplify. So for example, if I look at n plus 1 factorial, I realize that that just means n plus 1 times n minus 1 times n minus 2 times going all the way down to 3 times 2 times 1. But if you look at this part right here, well, that's actually n factorial. And similarly, if I had, say, like n plus 3 factorial, for example, well, that's just n plus 3 times n plus 2 times n plus 1 times n minus 1, going all the way down to 3 times 2 times 1. And again, there's an n factorial hidden in that guy too. So once you see I have a ratio of factorials, it's very convenient. So I could do something like, if I had to simplify, what is n plus 2 factorial divided by, say, n plus 5 factorial? And I needed to know what that guy simplified as. Well, I realized that this is just, the denominator is going to be n plus 5 times n plus 4 times n plus 3 times n plus 2 factorial. I can just stop where the numerator is, stop where the smaller guy is, and the factorials will continue. So these guys would cancel here, and this would actually simplify to a fraction that we know how to deal with nicer. So n plus 5 times n plus 4 times n plus 3. So it turns out just having a ratio of factorials is a very convenient thing to have, because you can simplify that thing to a rational expression very nicely. And when we're looking at rational expressions, we know how to take limits of those guys very easily. You just look at the highest powers, essentially. And in this case, you're always going to end up in a situation where the highest power is clearly going to be on the bottom, in which case the limit goes to 0, or the highest power is clearly going to be on the top, in which case the limit is going to be infinity. Right? So having the ratio of factorials is super convenient, which is why if you do see factorials in a series, the ratio test is one of the first tests that would come to mind. Well, right after the test for divergence, of course. You always see the test for divergence before any of these. But the ratio test would be a close second once you see factorials. Wouldn't you add an exclamation point after the n plus 3? At which stage?
In the last answer you just wrote out, in the denominator there.
No, because the factorial part gets canceled. The factorial part is here.
Ah, I see. Okay.
Right, this guy would continue to expand going down, but then the numerator is also going to expand going down. So literally the entire tail gets canceled. So there's no factorial left. It's just a nice rational function. So that was a second example using the ratio test. And again, technically, if I saw this on a quiz, man, it diverges, test for divergence, easy. What, does Jhevon take me for an idiot? And at this point, you're like, this kid, he has to wake up really early in the morning to fool me. That's what, of course, by the time Saturday rolls around, that's what you guys are all gonna say. You're gonna roll your eyes. What is Jhevon trying to pull right here? Like he didn't realize I would have seen this. Oh boy. And then you just realize it's test for divergence. Of course, if things were flipped and the e to the n was on top and the n factorial was on bottom, you'd realize that that actually converges absolutely, because here you'd have the n plus 1 in the denominator, the limit will go to 0, and that was always less than 1, converges. And that one you'd have to show some work for. But as presented, this is a straight up test for divergence problem. But I want to showcase this little trick to you, why the ratio test is convenient for factorials, because it allows us to simplify them to rational functions, which we can deal with very easily. So that's the ratio test. In theory, works on any test. Find this limit specifically, always this limit. And then if it's less than 1, it converges absolutely. If it's greater than 1, it diverges. If it equals to 1, you can't actually make a conclusion. And it's worth mentioning that if your an is a rational function, then you would always get L equals 1.
Jhevon?
Yeah.
What I want to tell you, if a student put on an exam that puts down, like, divergence by the ratio test, like, what's going to happen, by the way? Like, even if it does diverge by the test for divergence, however...
Well, let's say there's a problem that's worth 10 points, right? And you said diverges by the ratio test, but you don't show any evidence. Maybe you'd get like 2 out of 10 points.
No, like, if you show your work, like, if it diverges by the ratio test rather than the test for divergence.
Oh, you're talking about this particular example?
Yeah.
They would get the credit, like they would get full credit for it. But the thing, so I'm not going to punish them for doing it this way. However, that student would have wasted time. That student would put themselves at a disadvantage. Like I
So
wouldn't put them at a disadvantage
but
here,
if it
but
was a
they would put
multiple choice
themselves.
question,
Again, if you're thinking in terms of the ratio test, it's going to take you longer to figure out what the answer is, even if it's a multiple choice question. You would still put yourself at a disadvantage. It's going to take more time for you to go through this
I
than to just
understand if it takes a
notice.
lot of time, but if you were to like put like the instead of the supposed test for divergence is one of the options of the multiple choice. You normally multiple when it comes to multiple choice, it's either right or wrong. So if you pick like divergence by the ratio test, like
Yeah, well, I wouldn't put that as the option. I would just say converges or diverges,
okay, then
right?
diverges.
And then the student who does the ratio test, they're going to spend 5 to 10 minutes. And the student who sees the test for divergence, they're going to spend 10 seconds. And at the end of the day, the other student is going to be short on time. They're going to rush. They're going to either not finish the exam if they are inefficient with everything else, or they're going to rush and make silly mistakes that otherwise they wouldn't have made, all because they chose a method that was less efficient. These things all compound on each other, right? So it's not just, I'm just going to do the first thing that comes to mind. Just taking a couple seconds to figure out this is more efficient than that actually helps you a lot in the long run. So it's not a matter of just, oh, I can get it right either way, so I'm just going to do whatever way I want. Yeah, you can do that, but you are putting yourself at a disadvantage. So it's like, I want to go to the store across the street. You know what I'm going to do is I'm going to take a subway. I'm going to go somewhere else. I'm going to go to the airport. I'm going to fly to Europe, and then I'm going to fly back, and then I'm going to take the subway back and then cross the street. Why would you do that if you can just cross the street? You know what I mean?
You mean it's like taking a local train rather than the express, huh?
You really think that matters? That's the what you got? Well,
Is
it
that what you're
depends if
trying
it's
to
the local
say?
or the express. No, I'm saying doing one just doesn't make any sense compared to the other one. You'd both accomplish the same thing, but at much greater cost of effort and
Depends
energy
upon
and
which
time.
one's like, saves more time and energy, which is very, efficient
Yes,
and also very convenient.
yes. Anyway, the last test that I want to cover is the root test. So this is the last one in the list, the 9th series test. So this one is particularly useful when the guy looks like an exponential. So if you're a series, you notice that it looks like some expression raised to the nth power. This guy is often going to be very convenient to use. And again, the test for divergence wouldn't work out and so on and so forth, right? So this one, you do find another limit, but you find this particular limit. You find the nth root of the absolute value of the expression. Based on the value of that limit, you can tell whether something is going to converge or diverge. Now, if you take that limit and it's less than 1, you can conclude it converges absolutely. If it's greater than 1, you can conclude that it diverges. And if it's equal to 1, you can make no conclusions. Now, of course, the first thing that should jump out at you here is that this guy's very similar to the ratio test. The difference is just the limit that we're finding. But other than that, it's very similar. And one thing I want to point out is that that's actually more true than the typical student tends to realize. So I do want to emphasize that. The ratio and the root tests are indeed very, very similar. In fact, you can prove both of them are true using the same technique. You can actually prove both of them that work using a geometric series in the background. You don't have to know that. I'm not going to go over that. It's just too much time. And I can say this on top of this. These guys would always agree on their conclusions, right? So if the ratio test shows convergence, the root test is going to show convergence and vice versa. And if the ratio test shows divergence, the root test is going to show divergence and vice versa. And if the ratio test is inconclusive, then the root test is also going to be inconclusive. So if you're in a situation where, okay, here's a series and I try the ratio test on it, and you realize that it doesn't work, the limit equals 1, it's inconclusive, then you should not try the root test. because the root test is going to give you the same answer. The ratio and the root test, they behave very, very similarly, right? So even though you're looking at a different limit, the behavior of the tests are going to be very similar. So if one is inconclusive, the other one is going to be inconclusive. So that's one thing that you should be aware of here. So you would never actually do both the ratio and the root test for a single problem. It's because it's going to be a waste of time. There are other times where you might have to use several different tests to attack a single problem, but you're never going to use test 8 and test 9 in conjunction because they're both going to give you exactly the same kind of conclusion. So that's one thing that you do want to be aware of. That being said, this is the root test. Applying it is as simple as it looks right here. You set up this limit. If the limit is less than 1, it converges absolutely. And again, because we have absolute values built into the expression here. If the limit is greater than 1, it diverges. And if the limit is equal to 1, then you can't make any conclusion because you can get both convergence and divergence. What I have in red here is the 2 remarks that I just made. The ratio test and root test are very similar. So if one is inconclusive, the other one's going to be inconclusive. So don't try both. And they are useless when it comes to rational functions. So I have that bold and underlined here. So if you have a rational function, do not use either of them. You are wasting your time. Okay. You will always get the limit equals 1 if you plug in a rational function into the ratio or the root test. However, here's an example. You have some guy raised nicely to the nth power. Whenever you see that nth power there, you have a bunch of things raised to an nth power, or even a constant times an nth power is good enough as well. The root test tends to be very convenient. And again, provided that the limit doesn't approach something other than 0, right? So we're assuming that you already assumed the test for divergence and you realize it doesn't work out. So here's one. So this is our AN right here. So for this guy here, we have the series n goes from 1 to infinity of 2n plus 1 over 7n minus 3 to the n. First of all, you should recognize that that's an indeterminate form if you're trying to use limits. But this guy here, I'm going to think of this as my AN. So now by the root test, and why would I choose the root test here? Well, because I see that nice little nth power right there. By the root test, it's called the root test because I'm actually going to take a root. I'm going to look at the limit of the nth root of the absolute value of the term. So this is 2n plus 1 over 7n minus 3 to the nth power. Now notice here, let me actually write this down. So I would find the limit of the nth root of the absolute value of an, which is this. Now, what's nice about this is that the nth root and the nth power will cancel each other, which is why it's really nice when you see something like to an nth power. And then that just leaves us with the limit of 2n plus 1 over 7n minus 3. And what's that limit? Right, 2 over 7, ratio of leading coefficients. One nice thing about 2 over 7 is it's less than 1, which means the series converges absolutely. Ba-dow. And that's that. That's the root test. Right? That's the last test that we actually want to cover. So at this point, we've covered 9 tests. You can see them all at a glance in the table up here. That was at the beginning, right? Covered this guy. This guy here is the test for divergence, integral test, p-series test, comparison test, limit comparison test, alternating series test. Absolute convergence, that's not really a test. It's more of a process that you would go through that I'm going to talk about now. The ratio and the root test, right? So lots of tests, just like how we had lots of integration techniques, you have a lot of series test techniques. And so, of course, there is some potential for confusion or concern here because there are just so many things to try. How do you know? Like, how do you know not to end up in this situation where you do something that's just inefficient and you end up wasting time, or worse, you're trying to do something more complicated, you just make a mistake because it got too complicated. So you cancel something wrong or something. How do you make sure that you don't end up in that situation? We will talk about. But before that, I do want to mention this idea here. Figuring out absolute convergence versus conditional convergence versus divergence is going to be a very, very important thing. I mentioned that absolutely convergent series are very different behaving than conditionally convergent series in light of the rearrangement theorem. This makes that absolutely convergent series behave very well with calculus. Like, we can integrate them, we can differentiate them, and we can do all sorts of things with them. And we actually cannot do these things with conditionally convergent series. So it's very important that if I'm using a series in some application and I want to apply like some calculus to this application, I need to know that my series is absolutely convergent before I can apply any of these techniques. And so determining whether things converge absolutely, converge conditionally, or they diverge is going to be very important. And we often will have problem types that ask you just that. So you will have a problem type that is going to look like this right here. Determine with justification whether or not the following series converge absolutely, converge conditionally, or diverge. And yes, we're going to apply the series test that I gave you before, but it's with a different emphasis on it, right? So also remember what it means to be absolutely convergent. It just means that I put absolute values around all the terms and then apply a series test to that new series and it still converges, right? That gives me absolute convergence. If I put absolute values around the terms, but it doesn't converge, like we saw an example like that earlier. So in the alternating series test example, here was an example of a series. It converges by the alternating series test. However, if I put absolute values around it, it does not converge. So if with absolute values, it does not converge, however, it converges without them, we say that converges conditionally, right? And when it comes to doing a problem like this, the order in which you do things can be important. So here's the thing. The absolute convergence is going to be the gold standard. So whenever you're asked a question about does this converge absolutely, or does it converge conditionally, or does it diverge, you are going to want to check for absolute convergence first. Because if you check for conditional convergence, it's possible that it also converges absolutely, and you'll have to do an additional test. You are going to want to check absolute convergence first in general, because if it's absolute convergent, you don't have to check conditionally convergent, because if it converges with absolute values, it's definitely going to converge without. But the other way is not true. So there is a certain order you're going to want to go about these problems in terms of. Okay, so the process for doing an absolute convergence versus conditional convergence versus divergence problem type. There are really 3 steps that you want to consider, beginning, of course, with step 0, which is always the first thing you want to do. Look at the test for divergence, okay? You always do that for anything, right? You look at a series, one of the first thing you're going to look for, does it diverge by the test for divergence? Always the first thing you look for, okay? So you want to determine whether a series converges in one of these 3 ways. First thing you're going to do, apply the test for divergence. A lot of times you'll be able to eyeball it and tell. If the series is found to diverge, you just stop. The series diverges by test for divergence. You don't have to do anything, right? However, if the divergence test is inconclusive, meaning that the limit is actually 0, then you actually cannot tell. So now you would move on to the first step in this process. You want to check absolute convergence first. So you're going to put absolute values around the series terms, and then you're going to run one of the series tests that I taught you earlier. Then, if it does converge, you're going to say, well, the series converges absolutely by whatever test you used. If it diverges, then you move on to the next step. Then you're going to check conditional convergence. How do you do that? Well, you remove the absolute values, and then you check the series by itself without the absolute values there. And if that converges, you can conclude the series converges conditionally. And if not, then you can finally conclude the series actually diverges. So there's a 3-step process to go through, where really the first step is step 0. It's kind of something that you just always eyeball in your head. There are some important notes here that you should keep in mind. Remember, there are certain tests that have absolute convergence automatically built into them. So the ratio test and the root test have absolute convergence automatically built in. The geometric series test has absolute convergence automatically built in. Are you guys hearing me? I'm hearing interference. I think it's probably someone else. So the geometric series test, the ratio test, and the root test, they have absolute convergence built in. The integral test also tends to have absolute convergence built in because you have to be positive. So if you're doing one of those 4 tests, then the convergence is actually absolute whenever they work out. But not all tests are like that. You should remember the alternating series test only can show conditional convergence. There's a reason that I'm repeating this, and there's a reason that I put it in red both times. Okay? Okay. Oh, that's good. Little children learning about series. That's awesome. You should ask them the questions. Ask them, help mommy with this. Okay, so that's that. And we are going to run through these examples here. Yeah, the next Gauss, right? We're going to run through these examples here where I'm going to show you what it would look like to talk about one of these problems. But I think before that, I do actually want to talk about the process so that we can go through these problems a lot more efficiently. So as promised, I want to talk with you guys about how to actually approach series. How do you know you're doing what's most efficient, that you're going about it the right way? There's so many tests, like how do I know which one to do first, which one to do second? And I recopied the table here because I'm really going to expound on what this table tells you to do, but sort of in a step-by-step fashion. So that can be very helpful, I think. So let's just take a few minutes and run over that. It's not as many steps as with integration, but the steps are actually important. So general approach to determine if a series is convergent. Again, step 0, test for divergence. Always do that first. Look at the limit of an. Does it not approach 0? Because if it doesn't, it diverges. It's easy to see, so it's worth trying first all the time, right? If the test for divergence works out, it's going to be one of the quickest ways to get the problem done in general. So you always try to do that first, especially if it's something that you can just eyeball and you can tell, okay, the limit here is not going to be 0, so I can do it, right? So that's the first thing. When you see a brand new series, a random series pops up on a quiz, right? So the first thing you do is panic. I'm kidding. You don't panic. Don't panic. The first thing you do is like, remember training grasshopper. You say that to yourself, and then you immediately think test for divergence. If test for divergence shows it diverges, you're done. You're just like, it diverges. End of story. Move on to the next problem. Also, there are sometimes a problem would ask you specifically what a series converges to. So again, this is something that you're going to pay attention before you even start the problem. Just depend on how the question is phrased. If they ask you specifically what a series converges to, then it's either going to be geometric or telescoping, which for you guys means it's going to be geometric because I didn't teach you guys telescoping. So the telescoping series and the geometric series, these are the only tests that tells you specifically what it converges to. Remember, a geometric series converges to a divided by 1 minus r. You can specifically say what the answer is. None of the other tests can tell you that. They just tell you that it converges, right? So pay attention to how the question is being asked. So if you are asked what it converges to, then it's going to be geometric for you guys. So you just use the geometric series test. So that takes the guesswork out of it. Now, if the question asks about absolute convergence versus conditional versus divergence, you are going to use the method that I told you about here. So that would take some guesswork out of the way there. Okay, so assuming we're not in that situation, right? So everything I'm going to say right now, these are step 0, step 0, 0, step 0, 0, 0. For most problems, they're not going to finish the answer, but I might just throw a problem that one of these is going to be the answer just to see who's paying attention. But yeah, assuming none of these guys work out, how do you actually go about determining whether a series converges? Well, for one, see if your series has a specific form. So assuming none of the previous things I mentioned hold, there are some series tests that rely on specific forms. This means you can look at it and you can tell that, hey, you are in a specific form where I know a specific test that deals with that form. A geometric series is such a test. An alternating series test is such a test. And a P-series test is such a test. These guys have very specific forms that they can look like. A geometric series is going to look like one of the first two series here. An alternating series must look like that. And a P-series must look like this. And again, I am once again mentioning in red and in bold that if you're looking for absolute convergence, you cannot use the alternating series test. How many times have I said that in this lecture? I don't know. I'm pretty sure someone is going to actually try to use the alternating series test to talk about absolute convergence in the exam. I just know it, but I'm warning those of you who are actually going to listen to me. Okay, so there are some tests that deal with a specific form. These guys should be easy to spot because they're going to look like a specific form. Or you can just use a little bit of algebra tweaks to actually make them look like a specific form. So whenever that's the scenario, do that first. Just apply that because it looks exactly like a certain form. Nice thing about geometric series is that they always converge absolutely as well. So the first two series have a technique that give you absolute convergence. Another step, and these steps are in no particular order, it just depends on what you look like. If something is a rational function, or it's very close to being rational, use a comparison test. So I told you about the direct comparison test or the limit comparison test. When are those guys useful? If you have a rational function. Assuming it's not straight up a P-series, just think of this as a rational function. What you would do is you would compare to the guy that ignores all the lower powers, right? So you'd compare this to a minus that, which you know that this guy diverges. So you can use here like a limit comparison test, right? So you should look at that series and you automatically know what strategy you're going to apply. And here you can actually easily know what's going to happen because it behaves harmonic, right? The highest power on top is a square, the highest power on the bottom is a cube. So he's going to behave like 1 over n, which I know diverges, right? So I see this guy, and within a few seconds, you should be able to tell, oh, I'm going to do a limit comparison with harmonic series. Why would you do it with that harmonic series? Again, you would focus on the highest powers. Another scenario is when you have something that's almost like a rational function, like this guy, for example. So he's not a rational function because of the square root. But if I compare it to all the guys besides the highest powers, this is going to look like n squared divided by n to the 4th. So it can look like a rational function when I look at its limit form. Ignore all the lower powers. If I ignore all of these guys and just focus on the first two guys, then this is going to behave like that guy, which is a rational function. So it's almost rational. That you will realize, well, that's just 1 over n squared, and that, you know, converges. So
Call them on your phone, please.
Hello? Hello? Can you hear me? I don't know if that was directed to me or someone else. Can you guys hear me? Yeah, okay. So I think that was directed to someone else. All right. So yeah, that here, now I would just do, again, a comparison. And in this case, again, I would do a limit comparison because I'm not sure who is going to be bigger here. But if you have a rational function, or you realize that when you simplify and ignore ignore everybody by the highest powers, you get something that looks like a rational function, or even a ratio of power functions, something you can look like the P series as, that's a comparison theorem problem right there, right? So these two here are prime candidates for a comparison theorem. Now, as I mentioned here, if your AN includes factorials or exponentials, try the ratio test. Pretty self-explanatory, so nothing really else to say there. If your thing looks like something to an nth power, do the root test. Again, self-explanatory, nothing to say there. Just like, again, you're looking for a certain form. And also remember, both of these will give you the same conclusion. So if the one doesn't work, the other one is not going to work. So don't waste your time going over it. Now, if you can think of AN as a function where the function is continuous, it's positive and decreasing, then the integral test is a candidate. So if on top of that, it looks like you can integrate the thing easily. So if as a series, it looks complicated. However, as an integral, it looks easy. And of course, you have to be good at integration, I guess, for something to look easy. So an example was like with this guy, e to the 1 over n divided by n squared. As a series, that is very, very complicated. However, as an integral, that's not complicated at all. That's a substitution, right? Integration by substitution can kill this guy if it was an integral. So if it were an integral. So we did that here with the integral test. So if you realize that if I look at it as a function, it's easy to integrate, and it's continuous, and it's decreasing, and it's positive, the integral test is the prime candidate here. And that's pretty much it. Once you can actually talk about, once you have a random series problem and the test for divergence does not work, it's one of the first things you're going to look for. Other considerations is how the question is phrased. If you're asked specifically to what does a series converge, you should know it's geometric. So use the geometric series test. Telescope is another option, but we didn't cover that. If you're asked about absolute convergence versus conditional versus divergence, then you're going to use the method that I have in the last section, right? So you're going to check for absolute convergence first, do some other test, and check if it converges. If not, you check for divergence. Check for conditional convergence. Then you're going to look, does my series have a very specific form? Of course, you have to have all these specific forms memorized. Then you're going to check, is it a rational function? Or is it something that's close to a rational function when I ignore the guys that I don't care about? Then you should use a comparison test. Does the thing contain factorials and exponentials and/or exponentials? Then the ratio test is going to be a good idea. Does it have something to an nth power? Then the root test is going to be a good idea. Hey, is the thing easy to integrate? Then the integral test might be a good idea, provided that these 3 bullet points are fulfilled. You have to have those or the integral test does not apply. And yes, whenever you're showing that you're applying one of these tests, I do expect you to show that the scenario that makes the test valid is actually fulfilled. And so that's essentially the strategy. I mean, if you go through this 5-step strategy for series, you should be able to attack any series. So step 1 is to actually know this table. You want to have this table memorized. And believe me, you do enough problems, you're going to memorize this automatically, just by heart, just by practicing a lot. So I know it looks like a lot of information, but it actually gets really easy to identify these things in this table if you're doing enough practice. If you find yourself it's hard to memorize what's going on in this table, you're not practicing enough. You should actually do more problems. So once you have this table memorized, then this is the strategy that you're going to use to approach the series. Yeah, and that's how you would approach the series. That being said, I probably don't want to spend any more time right now because we're already over time. But what I'd want you guys to do is to actually try these guys for next time. So try these for tomorrow. We're going to run through them, and you're going to try to apply the strategy that I just gave you and try to apply it to these. Now, the question at hand here is to determine whether it converges absolutely, converges conditionally, or diverge. So you are going to apply this method right above here in light of the strategy that I just mentioned to you. And I'm going to include these guys on the PDF, so you can actually try this. But if you want, you can take a screenshot right now and do those.
Question about the test.
Yes.
So do we need to confirm with you about the morning or the afternoon session that we want to take on the test?
You only need to confirm with me if it does not work. So I am working under the assumption that everyone is fine with the afternoon time slot. So you would really need to reach out to me if that is not true for you.
When is the afternoon time again?
You want to like reserve between 12 and 3. So the test is going to be about an hour and a half. And for certain problems, I think I'm going to want you guys to upload scans of your work. So I'll give you like another hour and a half to get that done. Maybe an hour to get that done. So you should be able to finish with the test by like 2:30. At most. I mean, if you guys followed previous advice, you should be able to scan stuff in like 10 minutes. But and yes, to answer your question, if I ask you about, if I pose a question like is mentioned here, yes, you have to identify if the convergence is absolute versus the convergence is conditional. So in a problem like this, the multiple choice options would be converges conditionally, converges absolutely, or diverges, and you'd have to pick which one. And you'd probably have to indicate a justification for it, and your scans should show a justification for it. And yes, if you have questions about anything, you can email me at the class email. But yeah, try these guys based on what I covered before. So you're definitely going to want to follow this method here, but in light of the strategy that I gave you on the next page. And tomorrow's class, we will begin by running through these 4 problems, hopefully very quickly. And I will talk a little bit about tomorrow's plan. I'm going to talk about estimating series, and I might start power series. And yeah, but for now, that's it. Now you know all the series tests. You know about how to check for absolute convergence versus conditional convergence versus divergence. You also have the series strategies for how to know what to try first or second or third. So with that, you should be able to kill any series problem when it asks you about convergence. And we are going to wrap up there. So again, take a screenshot of that, and we are going to wrap up there. That being said, good night, everyone. Hope you guys have a good rest of your night, good rest of the week. Good luck this weekend, and we'll continue. We'll continue trying to get that bread. So without further ado, I'll post the video and the PDF, and I will see you guys in the next one. So ciao.